All of the examples we've looked at so far have had even number of electron pairs, but you don't have to have an even number of electron pairs. So let's talk about an example of a molecule that has an odd number of electrons, and let's look at nitrogen dioxide. Now, if you have an odd number of electrons, it's called paramagnetic, or a free radical is sometimes what it's referred to, and NO2 is a great example of that. So let's build a Lewis structure for NO2. So like before, central atom, usually listed first, lowest electronegativity, etc. It's going to be nitrogen, no question. Now, valence electrons. Nitrogen is 5, and oxygen is 6, and there's 2 of them. So 6 times 2 for the oxygen, 12, plus 5 for nitrogen, 17 valence electrons. So this is definitely a difference now, because if you have 17 valence electrons and you try to divide it by 2, so what I do personally in these kind of situations is if you run into an odd number of electrons, 17 divided by 2 would be 8 pairs plus 1. And this plus 1 just helps me remember that we're going to have one extra electron kind of floating around. And that extra electron has to have its own room. All right, it can't be bonded with any of the other pairs. And I'll show you this here in a little bit. So what we would do is we put nitrogen in the middle, oxygens on the outside. You'd start by drawing a single bond between the oxygens to keep them connected. You'd then give each oxygen a filled octet, i.e. 3 lone pairs around it. But if you do that, you're left with then an oxygen, nitrogen, oxygen, where the oxygens have their octet, but you've got this 1 electron left over. So what you would do is you'd put the odd electron on the nitrogen, all right? But if you look at this structure now, nitrogen doesn't have even anything close to an octet. It has 2 bonding pairs and a lone pair. And it needs to have at least 4 types of things, pairs, whatever, around it. So in the final version, which is shown in the lower left right there, that one of the lone pairs comes from the oxygen on the left to make a double bond, and that would make the N happy. All right, like this nitrogen right there has a double bond on the left, a single bond on the right, and a lone pair, so 4 pairs around it. But really, there's no reason why you couldn't have taken that lone pair from the right oxygen. So you could also have this structure right here. So this particular molecule is what they call a resonating molecule. And it's another thing we'll talk about a little bit more here in a little bit. But before we go into resonance, paramagnetic things are just a lot more reactive. They're attracted to magnets. They do different things that the other things don't. Most of the materials around us are diamagnetic, and diamagnetic things are not attracted to magnets. So when you have a paramagnetic molecule, you have to be careful, all right? It'll do things that the diamagnetic things won't, and you can draw Lewis structures with them. The important part is just give that lone pair its own space. So if nitrogen can handle 4 things around it, like 4 bonds, that lone electron is going to take up one of those 4 places. You wouldn't try to jam it in with another one. You wouldn't want to make 2 double bonds to the oxygens, because then nitrogen would have 4 bonds and a lone pair. That would be more than the octet. So the lone pair just takes up one of the pieces in the octet. Let's talk a little bit more about resonance, why we did that. So sulfur dioxide is SO2. Let's do a Lewis structure for this. Central atom, sulfur, definitely. Oxygen's on the outside. Sulfur and oxygen have 6 valence, so 6 times 3 essentially is 18. Divide that by 2, 9 pairs. Put the lone pairs around the atom. You can see that oxygens have full octets, but sulfur with a lone pair and 2 bonding pairs does not have an octet. And sulfur wants to have an octet. The only ones that can go under are boron, beryllium, aluminum, those kind of things. Sulfur is not in that list, so sulfur needs an octet. So we would make a double bond. You could take an electron pair from the left oxygen to make a double bond, but you could also take one from the right to make a double bond. Either way is fine. So the question is here, which way is better? Is it better to take one from the left? Is it better to take one from the right and make a double bond? And this leads into the idea of what's called resonance, because really, energetically, there's no difference taking a lone pair electron from the left to make a double bond, or taking a lone pair from the right oxygen to make a double bond. They're energetically similar. So this leads to what we saw with the NO2 example. This leads to resonance, all right? And resonance is when you have more than one possibility for a double bond. Now, in reality, you don't have two separate molecules. You have like 1.5 bonds on the left and 1.5 bonds on the right. So you see a hybrid, a mixture of these two resonance forms. But to make sense of it in our world, people will usually draw both resonance forms, and then the hip chemist will know that the actual version is a mixture of the two. So for the NO2 example then, there would be oxygen on the left with a double bond, and then oxygen on the right with a double bond, and it would hybridize back and forth between them. You'd have a 1.5 bond. When it comes to resonance structures, sometimes there will be a question as to what is the better resonance form. And better here means more stable, okay? And chemists use what's called a formal charge to determine the most stable Lewis resonance form. And these can be actually pretty helpful. Now, formal charges are a little bit weird, but it is a powerful tool in the chemist's arsenal when you're creating a Lewis structure, so it's cool to think about. The definition of formal charge is kind of strange, but what you're going to end up doing is you're going to find a formal charge, which is a type of a charge on each atom in a Lewis structure. The Lewis structure with the most zeros is going to be the winner, all right? It's going to be the best Lewis structure possible. So how do you calculate formal charge? Great question. Formal charge, there's different ways to do it, but what I like most of the time is I use the fact that the formal charge on each atom is going to equal the group number of the atom minus the number of bonds minus the number of lone pair electrons. And so you'll calculate this formal charge on each atom in the Lewis structure, and you want to have the most zeros possible. Now, if you've done everything right, when you add up all of the formal charges in your molecule, the sum of the formal charges must equal the ionic charge. And I'm sure at this point, this is like kind of gobbledygook to you. So let's look at some examples and figure out how you would use formal charges to tell what the best structure is.
Formal charge calculations can often help us identify the most stable isomers of molecules. Consider the isomeric compounds, hydrogen cyanide and hydrogen isocyanide. Both structures have octets of electrons about carbon and nitrogen. The formal charge on carbon in hydrogen cyanide is 0. Similarly, the formal charge on nitrogen is 0. In hydrogen isocyanide, the formal charge on carbon is -1. The formal charge on nitrogen is +1. Because the formal charges are non-zero in hydrogen isocyanide, we can predict that this isomeric form is less stable than hydrogen cyanide, as found to be the case.
So this is an example of how you can use formal charges to tell what is a more stable structure. And on the right-hand side there, we have hydrogen cyanide in the top, which is an H followed by C and then N. And in the lower part there, that's hydrogen isocyanide. It's a hydrogen with a nitrogen in the middle followed by carbon. Now, if you followed electronegativity rules, carbon would go in the middle because carbon's the lowest electronegativity. Nitrogen would be on the outside, the higher electronegativity. But you can actually make the isocyanide compound where the nitrogen's in the middle and carbon is on the outside. So let's see if electronegativity helps us out here by predicting a stable molecule or not. And so what you would do is you draw the Lewis structure and then calculate the formal charge. So for hydrogen, which is pretty easy, hydrogen has a group number of 1. That's the 1A on the periodic table. It has one bond, the hydrogen-carbon bond. So we'd have group number 1 minus 1 bond. Hydrogen has no lone pair electrons. So 1 minus 1 minus 0, that's where the zeros come from. So both of these hydrogens have a formal charge of 0. No big deal. If you go to the carbon in the hydrogen cyanide, that carbon is a group number 4. It's 4A on the periodic table, so 4. 4, and that carbon has 4 bonds, 1, 2, 3, 4 sigma bonds, no lone pair electrons. So it would be 4 minus 0, formal charge of 0. Cool. Now the nitrogen on the end of hydrogen cyanide, group number 5, it has 3 bonds to carbon, so 5 minus 3, and this has 2 lone pairs. And notice that you count each lone pair electron in this calculation. It's not the lone pairs total, it's lone pair electrons. So you'd go 5 minus 3 bonds minus 2 lone pairs, formal charge of 0. Now if this is a good Lewis structure, and it's a good thing, all the formal charges together should equal the charge on the molecule. 0 plus 0 plus 0 equals 0, and that's good because HCN is a neutral molecule. All right, so this is a good resonance structure. But now let's look at the lower example. This is hydrogen isocyanide. Now hydrogen is still 0, so that's not a big deal. 1 minus 1 minus 0. But the nitrogen in the middle now, nitrogen's group 5. That nitrogen has 4 bonds, 3 to carbon and 1 to hydrogen, 5 minus 4, and no lone pair electrons. So this formal charge, positive 1. The carbon on the end, group number 4, 4 minus 3 bonds to nitrogen, minus 2 lone pair electrons, 4 minus 3 minus 2, minus 1. All right. Now, if you add those 3 formal charges together, 0 plus 1 minus 1, they all go to 0. And that's good because hydrogen isocyanide is also neutral. But here's why chemists think that hydrogen cyanide, the top one, is more stable than hydrogen isocyanide, the bottom one. You have more positive ones and negative ones in this molecule than you do in the hydrogen cyanide. All of those are 0, and the bottom ones are negative. So the positive one, negative ones in the lower structure, those are like beacons, if you will. Positives will attract other negative things, and negatives will attract other positive things. So that nitrogen with a positive one in the middle will start attracting negative things like chlorides or oxides, stuff like that. And on the other hand, that negative carbon on the far right, that'll start attracting positive things to it. So HNC, the hydrogen isocyanide, will be more reactive. It has more positive and negative charges to it. Hydrogen cyanide at the top, everything is 0. It's like stealth mode, all right? Nothing positive or negative would see it, at least not readily. So this is the advantage of formal charges. Because there's more zeros, we would say hydrogen cyanide is more stable than hydrogen isocyanide. And it is. Hydrogen isocyanide, you have to keep really cold temperatures. You can't let it react with anything because it's very, very reactive. This is the advantage of formal charges. Here's carbon dioxide. Now, earlier I just showed it with 2 double bonds, and if you figure out all the formal charges, everything goes to 0. So oxygen on both the left and the right, because it's the same environment, 6 minus 1/2 of 4. This is 1/2 of the bonding pair electrons. I would usually just use 1 minus 2 to represent the number of bonds, but you can either count the bonding electrons or you can just count the number of bonds, either way. So I would say 6 minus 2 minus 4 gives you 0. The 4 on this side, those are the bonding, the lone pair electrons. And each oxygen has 4 lone pair electrons. But this number right here, I would just say the number of bonds. So 6 minus 2 bonds minus 4 gives you 0. You can also count the individual electrons. It's your call. Either way, both the oxygens are 0. And the carbon in the middle, 4 minus 4 bonds, or 1/2 of 8 if you're counting the electrons, no lone pair electrons, that carbon is also 0. All the formal charges together, the 0 plus 0 plus 0 equals 0, which is good because CO2 is neutral. The more zeros you have, the better. This is all zeros, so that means it's a good structure. It should be stable. And why we're doing this is because you can actually draw CO2 with a triple bond. Now, the carbon in the middle is the same electronic environment. All right, 4, group number 4 minus 4 bonds, it's going to be 0. But now the oxygens oxygens on the left and the right-hand side are different. Oxygen with a single bond ends up with a formal charge of -1, and oxygen with a triple bond ends up with a formal charge of +1. So if you add those formal charges together, you still get 0. All right, carbon is 0, -1 for the right-hand oxygen, plus +1 for the left-hand oxygen. You still go to 0, but it's not as good as the previous CO2 because you've got negative and positive ones. They're like little magnets that attract the opposite charge to them. So that positive oxygen will attract negative things to it. The negative oxygen will attract positive things to it. So people feel that CO2 with 2 double bonds is a better Lewis structure than if you have a triple and a single like you do here. This sheet sometimes people find helpful. These are ways to represent the best formal charges, and best in this case means formal charges of 0. So for example, if you have a boron with 3 bonds to fluorine or chlorine or whatever around it, that's going to give it a formal charge of 0. But you do sometimes see the structure on the left, which is a boron with 4 bonds. That gives it an octet, and that actually gives it a formal charge of -1 on the boron, so it's not as happy. All right. Carbon we're going to deal with a lot, and these representations here are all carbons with 0 formal charges. And you can notice that most of them are like 4 single bonds, or a triple and a single, or a double and 2 singles, etc., etc. I would ignore the carbon with a lone pair. That's a very rare kind of carbon. Carbon with a lone pair is called a carbene, and they're very reactive, but officially that would be a formal charge of 0. But you wouldn't usually see a carbon with a triple bond and a lone pair. That would give it a negative formal charge. Or you wouldn't see a triple bond carbon with nothing else on it. That would be a positive charge. So sometimes this is a handy thing to look at. We'll see the oxygen usually has a double bond or 2 single bonds to make it happy. The halogens are usually a single bond, etc., etc. This is just kind of a quick and dirty way to know your formal charges without calculating them. And again, the more zeros you have in your molecule, the better. So let's go back to boron trifluoride. Boron trifluoride, we listed it with 3 single bond fluorines. But in reality, we could have made a double bond to fluorine. All right, that would have given boron a double bond, and it would have been happy and have its octet. But oh wow, when you figure out the formal charges, fluorines with a single bond and 3 lone pairs are going to have a formal charge of 0. But if you start sharing electrons with fluorine, fluorine ends up with a +1, and then the boron, which is group 3, ends up with a -1 formal charge. So you start having weird formal charges when you start sharing electrons. That's why boron, aluminum, gallium, they're totally happy being just less than an octet. They have 0 formal charges. Fluorine, to the most of the time, like never makes double bonds. I don't know of any stable structure with a fluorine double bond. All right, fluorine is the electron king. It wants electrons more than anything else. So you really want to stay away from making double bonds to fluorine. Now, once in a while, if you're like in the lab with high temperatures or electric fields, you can do things with fluorine double bonds. But 99% of the time, and all stable structures, as far as I know, fluorine will never make a double bond. So here's a question you might see. It says determine the formal charges on the formate ion. This is CO2H with a -1 charge. And I'd like you to figure out the formal charges on the oxygen on the left, the carbon in the middle, and the oxygen on the right. Well, if you look at the oxygen on the left, that oxygen has 2 lone pairs and 2 bonds, and it's group number 6. So formal charge for that one would be 6, which is oxygen. I would subtract the 2 bonds to oxygen, and you subtract each lone pair electron, so that's 4 total. It's going to have a formal charge of 0. Cool, stable. Carbon in the middle, group number 4, it has 2 bonds to oxygen, a single bond to hydrogen, and 1 bond to the other oxygen, 4 bonds total, and no lone pair electrons, so it's going to have a formal charge of 0. But the right-hand oxygen, still group number 6, it has one bond, but this has 2, 4, 6, 6 lone pair electrons. So this is going to have a formal charge of -1. So if you look at all those answers right there, it's going to be answer D. Now, the sum of the formal charges must equal the charge on the molecule or ion if there is one. And this thing has a -1 charge. So if you go 0 plus 0 plus -1, it equals the charge, which is -1 on the molecule, and that's good. So if you have a molecule with a charge, something is going to be non-zero, all right? And in this case, it's that oxygen with a single bond. And by the way, hydrogen is formal charge of 0, 1 group number, -1 bond, 0, okay? It's that oxygen, which is going to be the -1. So if you have an ionic compound, then something is going to be positive or negative.